Hello, class. I'm just checking my microphone and everything, and I have been gone, although to you, of course, I haven't been gone at all. This, I think, is lecture 10, but I have taken a day to grade, about a day and a half to grade all of the final exams from electromagnetic field theory, which is a course that some of you, I'm not sure if all of you are going to be taking electromagnetic field theory. I'm not sure if it's in both of the 2-degree programs. I believe it's only in the electrical engineering program that you get electromagnetic field theory. Fantastic course. I love teaching electromagnetic field theory. You get a lot of the magnetostatics and stuff in like motors and controls, your power course, but the understanding electromagnetic waves and Maxwell's equations, and actually even more than that, understanding that they're not Maxwell's equations. Actually, only one half of one of the 4 equations has anything to do with Maxwell. But yeah, it's a great course. So I finished that, and so now we are back to this. And what I want to do is, and really what we're doing here, this is something that all electrical engineers have to do when they're learning the fundamentals of network theory 1, is they've got to hone their skills at just, series, parallel, figuring things out, figuring out where nodes are, learning how to expand out a schematic from, what you find on a printed circuit board, which of course is what we did with this, looking at the 3 nodes, applying Kirchhoff's current laws. We could also, and we did before in an earlier lecture, look at the actual loop for Kirchhoff's voltage law and see that those, of course, also are conserved. The voltage increases, voltage decreases, going around a loop, and we've got loops here. Only one real interesting one. You know what I mean. So we're going to look at that. We're going to use that information, use the laws, use the current and voltage divider things to figure out what is the current going through all of these. You can see that we've already found the current going through several of them, right? So we know what the current is. I'm trying to remember what I think R1, and then, oh, I've got it written on the last page, but I've written all those down here. And we know what the voltage is up here. I'm just going to write this in again. That was 25 volts. That was V sub A, and then V sub C, which is our voltage right here, was 8.88 volts. We haven't figured out what our voltage is here at voltage at B yet. I believe this was B. I should probably go back and check these, but I'm pretty sure that this is how we did it, because we looked at the voltage drop across that 120 ohm resistor, right? And wouldn't you know it, I forgot to write all the numbers down. I'll tell you what. Just a second. Let me actually get all the numbers and everything right to. I'll be right back. You won't even know I'm gone. See, look at that. I'm back only an instant later, but it was 27 years for me. No, I'm not Rip Van Winkle. So, yep, I put all of the numbers in here. Of course, this is number 1, and then 2, 3, 4, 5, 6, 7, 8, just so that you've got the numbers down that we had that are the numbers down here, because I didn't put them relative to their resistors. Okay, I just realized another thing. I'm going to pause this and put my timer on. Excuse me. Yep, I had a little sip of water too. So I am back. And what we want to do is continue filling out the table of required voltages and currents that we've got through out our example here, and really just a skill building problem, as you can see from the original lecture that we had this with. All right. Now, uh, if we look at this, we know now what the current is flowing through the 120 ohm resistor. And that brought us here to the 8.8 volts that we have right at point C. And you can see now we've got the current that's flowing through here. So we know the current's flowing through here. We know current's flowing back through here, right? We also know that current is flowing back through this 330 ohm resistor and flowing in through this too. So we can figure out what the current is that's flowing through this 330 ohm resistor, number 5. So let's do that. So I sub 5. And what do we know about the characteristics of Ohm's law? Let me just write Ohm's law again. Wherever I can write it, I like to write it. V equals IR. And let's not forget our power. P equals IV. And really, like I said, it's just those two equations. If you go and teach in high school, or you go and your kid's learning in high school, he'll love P equals I squared R. I always loved P equals I squared R. It just rolls off your tongue, doesn't it? P equals IV just doesn't seem to do it for me. But how can you remember these two? I remember this as ver. You just got to remember where the equal sign is. Ver and piv. Ver, piv. Yeah, I mean, just remember the equal sign is right after the first letter, and you've memorized the two things, and that also gives you the other two power equations: P equals I squared R and P equals V squared over R. Have I said that enough times? I think you've remembered the other renditions of the power equation. All right, let's find out what I5 is, and here's what I'm saying. Where is the current flowing? So we know that the current is flowing out here, right? And we figured out what that total current is at I1. That's 400, and yeah, I didn't have a good pen when I wrote that down. 416.667 or 0.66 milliamps, right? That's a milliamps. Boy, it doesn't look very good. Milliamps. So that's the total that's flowing in to this point right here, that first junction, that first node that we have, isn't it? So the current is now going to be splitting up, and the current that's going on is going to be less. So let's look at that. We now know that current in that first one at that 100 ohm resistor that's going to be coming out, that's I sub 8, is 92.6 milliamps. And we know that at the current through I7 is 250 milliamps. And what that told us was, okay, that current is already coming out of the total 416.66. Now, where's the next current? We knew that the current that came back through here, had to all sum up to the total current, 416.66 milliamps, right at that point. Let's just sort of look at that again just for a second so that we can see how what the summation of currents at that node is like. Because we know all of I'm just going to put that resistor there, but whatever, we know it's a resistor. We also know that we've got resistor 4 here, right? So that's resistor 4, that's resistor 6, and then we have resistor 5 right there. Does everybody see that? Now we know a couple things. We know that as we were going down here, we figured out already. I'm not going to go back. You can look at the last lecture if you want to see how we calculated at that last node, right? The node that was down here. I'm going to actually draw that node in, as I have done before, with blue, right? Now, that's a node, but it's sort of a boring node because it's 0 volts. So, but that node, current was flowing back into that node through those two resistors, the 100 and the 270 ohm resistor. It was flowing back in. The only thing that was stopping it from short circuiting out were those two resistors values. right? So they've come back. We know that that current, those two currents then have come back into that main current that's going back into the thing. And we know what that is. It's 416 milliamps, isn't it? Right? So we've got that current that's going back into that. And then we've got these that are flowing into it. So we know that what's going onwards from there is going to be less these two quantities, the 250 milliamps and the 92.6 milliamps that have come out and have gone back into the main river, if you want to think of it, river of current flow. Not electron flow, though. Electron flow, of course, is opposite to current flow. So let's get back to this. So we know that those two currents have come out of there. We know that the only current that's left to go in there is the same current that we figured out is coming in from resistor 6. So we know what this current is up here. We also know what the voltage differential is across this resistor, right? Resistor 5 or the 330 ohms. Let's just write that underneath. 330 ohm resistor I sub 5. That's what we want to find out. What's our voltage differential? V equals IR. Well, let me just put that down next to it. Doesn't I equal V over R? Of course it does. So we've got our voltage differential, which is 25 volts minus 8.88 volts, which we've already, like I say, that was in the previous lecture. That's our voltage differential across that 330 ohm resistor, and it's a 330 ohm resistor, right? I equals V over R. Well, that's what we've got right there. So now all we have to do is take 25 minus 8.88 and then divide that by 330 ohms, and that gives us 48.85 milliamps. Oh, just a second. Oh, class, I'm sorry, just my head of department shot something to me on a text message, or actually it was like an invitation for one of these faculty meetings or whatever. So I just wanted to look at it to make sure I wasn't supposed to be at a faculty meeting right now. And I wasn't. It's August 14th, which is far away. So we now have I5, and we can put that in. So 48.85 milliamps. Right? Does everyone see how we got that? So we now know what I5 is, and we can draw it on here. Let's put that in blue. We know what's going back. What's going back is 74.1 milliamps. So this is 74.1 milliamps. And we know that coming into that node, we've also got 48.85 milliamps. Right? Oh yeah, that's a point, 48.85. So if that's coming in and that's going out, what that means is that this has to be coming in too, doesn't it? And what is the voltage using Kirchhoff's current law? Yeah, what is, I shouldn't say, did I say voltage? I said, I'm getting ahead of myself. What is the current that's going to be flowing into that node? We know that the summation of currents into the node has to equal 0, right? So we've got 74.1 milliamps flowing out, 48.85 milliamps flowing in through I5. What is I4 going to be? I think everybody can see that I4 is a 470 ohm resistor, but I4 is going to have 74.1 minus 48.85 milliamps flowing through it. I think everybody can see that. So 74.1 milliamps minus 48.85 milliamps. And in this regard, you can work in milliamps because you're just adding and subtracting. It's not like you're using it in a quotient or a product. In those cases, you would want to switch it back into its original form of amps, which is the real combination of primary units, right? Because here you've always got to use that times 10 to the minus 3, and that gets, I mean, you've got to put it in there. A lot of people don't. They just multiply it through by milliamps and think, oh, later on I'll do it, I'll divide by 1,000 or whatever. And in fact, they end up dividing, and whether it should be multiplying and multiplying where they should be dividing, and the spaceship goes off into nowhere land. So what this leaves us with is 25.25. How appropriate is that? Milliamps. So there you go. Now we have I4, don't we? 25.25 milliamps. Right? Now that also tells us something very interesting too, doesn't it? Because now I know the amount of current that is flowing back through that R4 resistor. And so if I know the current flowing through the resistor and I know the resistor value, then I should be able to find the voltage drop across there, right? And the voltage drop, of course, would be in this direction because that's the current flow. So my voltage drop is going to be across here. And that means this voltage will be higher. Voltage at B will be greater than the voltage at C, which is what we would expect anyway. I'm sure that you realize that from the very beginning. So we now know how much that's going to be, though. So what we can find next is the voltage at B, right? Because the voltage at B is just the voltage at C plus the current that's flowing through the 470 ohm resistor, and we know what that is. That's 25. I'm going to put 0.02525 amps. And why am I doing that? I think everybody knows, because I'm going to be using this in a product. So I want to actually switch it back into the combination of primary units, or a primary unit, which is amps, and we know amps is a primary unit. So I have no problems there. And then I want to multiply this, right, by my resistance of 470 ohms. And we know that ohms are already a combination of primary units, so we don't have to worry about using that. But we'd have a problem using it if we were using milliamps, because all of a sudden, where do we put that times 10 to the minus 3 or times 10 to the plus 3 or whatever? People always seem to make mistakes along those lines. So let's get back to this. So we've got the amperage and the resistance. So 0.02525 times 470 ohms is 11.87. 11.87 volts. Oh, excuse me, I put that in the wrong place. Let's put that down here. 11.87 volts. So we know what V sub C is. That's 8.88. And if we add 11.87 volts to that, I'm just going to, I want to point something out to you, because you're engineers and you'd love that. This thing, was broken. The tape had come out, and somehow it had gotten open, and so I took it apart, because I'm an engineer. I took it apart, and I wasn't even sure how it all went back together again, but I figured it out. And then I realized that this wheel wasn't enmeshed. You see the gears in back, that those two wheels weren't really enmeshed well. And then I just put it together. But then I realized that it was a design flaw too, because you have to really hold it right at where those two wheels are, and then it works perfectly. But if you don't, which most people don't, they hold it, you know, here, 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 and here, because they're not engineers and they're not really seeing how the mechanics of this work. They would just throw it away. Whereas I've got $1. I don't know. I'd say $1, maybe $1 more out of that, right? And that's how it is all, you know, throughout life when you really know the math. Well, if we add those two together, I get 20.75. 20.75 volts. That's what my voltage at B should be. So let's put that in there. 20.75 volts. All right. All we need now is I2 and I3, and those should be easy because we know what the two terminal voltages are on both of those two resistors, right? So let's just figure those out. We'll figure them out one at a time. I think that I2 is 390. So I2, let's just do that one. The difference in voltage is 25 volts up on top minus 20.75 volts below that. And then we're going to divide that by the resistor value, which is 390 ohms, right? So that really leaves us 4.25. 4.25 volts divided by 390 ohms is 10.90. 10.90. I'm going to put a line over that 0 because it's a significant digit. I want everyone to know that. You know, milliamps. Okay, and then we can do I3 because we've got the same thing. We've got 4.25 volts. That's our voltage differential on top. And then instead of 390, that's going to be 220 ohms, right? So 4.25 volts divided by 220 ohms is 19.32 milliamps. All right. Everybody just assumes that the 2 is always, you know, it's just the 0. That's why you put a line over the 0. You'll see that in work that you come across, plans and stuff like that throughout your life. All right, so now we know all of the currents that are going through all of these various resistors here. And they should all add up, shouldn't they? Because we know that the current that's coming back through the 470 ohm resistor, which is 4, is 25.25, right? And then we've got 10.9 and 19. Wait a second, how is that working out? What did I do wrong here? 25, I4, 25 point, just a second, let me look at this. Just a second. Hello, class. I am back. And as a matter of fact, I have done a lot of interesting things in the meantime since I was last here talking with you. And you might notice that I have changed a couple numbers here because no, I did not find that I had made a mistake. Actually, all of the analysis that we've done is perfectly correct. However, I did not use enough significant figures. And I want to show you what, you know, just a small change. For instance, this right here was when I did it on the simulator, was 8.92, right? And I've got 8.88. And you think, well, that's really not that much difference. But I think it was, yeah, 8.9 something or other. But anyway, what it did was it changed this from 48.85 to 48.45. And I had also found out that when I was working with the 74.7 or 0.1, that was actually a 74.5. 28.7. And so what that did is it changed the outcome here as far as the milliamps go, just by a little bit, from 25.25 to 26.2, so almost an entire milliamp. And so I placed that back in here, and I found out that our voltage there actually isn't 20.75, it's 21.2. And, you know, working all of that out. And in fact, I only found that I had lost like 5 milliamps in all of the analysis that we had done. But I thought, well, that's significant. And in fact, I found out that no, it was just propagation of calculator error, because instead of using 5 significant digits, I only used 4 significant digits at most places. So I just wanted to point that out. And so actually, yes, we did get down to the right amount. This actually comes to 26.2. I'm going to just put that in there, milliamps. And this is 48.45. But still, you know, minor changes. We have 9.45 milliamps for I2 and 16.75 milliamps for I3. And so there you go. We've got all of our various currents and voltages. Now that I should change. This one is really 21.2. So that's a little bit, you know, changed, but still minor differences compared to what our full analysis of that entire circuit after the simplification occurred was. All right. Now, what I want to do after that is I want to look at the power that's being used. Now, let's just look at all of these resistors. Let's say that all the resistors are 1/4 watt resistors. So let's look at the voltage that's across these resistors, and you're probably saying, hey, you know, that's got 75 volts across it. So what is the power that is going through the 180 ohm resistor? How could I determine that, right? Power equals V times I. So if we look at the amount of current, well, that's maximum current going through there. So that's going to be 0.41667 amps that's flowing through there. And we know that the current, or that is the current that's flowing through, we know the voltage across that is going to be 75 volts, the largest voltage differential in our entire circuit. And the real question is that going to be more than 1/4 watt, right? Is that going to be volts times amps equals watts, don't they? That's right, volts times amps equals watts. So 0.416667 amps times 75 volts is 31.25 watts. 31.25 watts. God, you know, I don't think our 1/4 watt resistor is going to work there, right? How about the rest of the circuit? You know, if we look at the rest of the circuit, we can see that there's a lot of current that's flowing through that 100 ohm resistor right there. So what is the power that's flowing through the 100 ohm resistor? Well, again, power equals VI. So the current across, the voltage across that 100 ohm resistor is going to be 25 volts. Not as much as the 75 volts, but still quite a bit. And then the current flowing through that resistor is going to be 0.250 amps, right? So we have 25 volts times 0.25, or 1/4 of that. And I think everybody can see that that's going to be 6.25 watts. Still much larger than the 1/4 watt resistor that we use in laboratory, right? So as we go down through there, I could keep doing this for each of the individual resistors there, and you can see that the current is going to keep dropping and dropping and dropping as we go along. So the voltage will pretty much will stay the same, especially for the next one, but the current is going to go down. So we keep losing current each time we're looking at one of those resistors as it goes down through that thing. And we've also found all of the various voltages at the different areas. Remember to use 4 significant digits when you do it. You know, I want to try something else because no, yeah, I don't know. I'd have to. I want to share another screen or whatever that I have up here, but I don't know exactly how to do it. I'm going to have to work on that, and I'll get back to you because I've done this in a simulator as well. And in fact, maybe the next class I'll start up with the simulator. Although I want to talk, we're getting up to for the next class. Let's just write that down. The next class is really going to be on Y and delta connections, you know, because there's some things that aren't series and aren't parallel, and we want to use Y delta exchanges to, you know, simplify those circuits. And that's what we'll be talking about in the next thing. And I also want to show you the simulation because I'm sure that you're going to want to simulate a lot of circuits to sort of see what the voltage is. And of course, great tool to use. You can use it online. I believe that we also have licenses to use it online from Wentworth. It's free. And then I also believe that we have some type of license when you're back in that you can actually get a copy to put on your computer. Maybe you can download it. I haven't looked into that, but I'll try and show you the simulation next time after I work with Zoom to figure out how to do that. All right. Uh, but I think we're up to speed now. We're going to start to get into some more difficult types of circuits. We're starting to get into, you know, analysis methods too. And we're going to keep moving in that regard. Moving up to through chapter 3 now. We've really covered just about everything in chapter 2. All right. On to the next lecture.